Hey everyone, and welcome to The Explainer. Today, we're unpacking the invisible chemical forces that literally dictate the physical properties of our everyday world. I mean, from the food you eat to the rain falling from the sky, there is a hidden tug-of-war constantly happening right in front of you. So, let's dive right in and uncover the delicate chemical balancing act of acids, bases, and salts. Here's a quick look at our roadmap for today. We'll be covering meat acids and bases, the chemical battlefield, neutralization, the science of salts, lab preparation, and finally, real-world chemistry. All right, Section 1, meat acids and bases, opposing forces of nature. Now, before we get bogged down in the complex equations, let's actually anchor these concepts in things you already know through your own senses. The word acid, it actually comes from the Latin word acidus, meaning sour. Think about that sharp, puckering bite of a lemon. That's literally citric acid reacting with your taste buds. On the flip side, we have bases. If you've ever accidentally gotten soap in your mouth, you know bases have this distinct bitter taste and a weird, slippery, soapy feel. But in chemistry, it goes way deeper than just taste. Acids are defined by their ability to yield positive hydronium ions in water, while alkalis, which are just soluble bases, yield negative hydroxide ions. To really understand these forces, we rely on two foundational theories. First up, the Arrhenius theory. This tells us that acids are substances that dissociate in aqueous solutions to give positive hydrogen ions. Simple enough, right? But the Lowry-Bronsted theory takes it a step further. It basically frames this entire chemical interaction as an ongoing game of give and take. In this theory, acids are proton donors. They've got a proton, a hydrogen ion that they are just eager to give away. Bases, on the other hand, are proton acceptors. They are literally waiting to grab that exact proton. So what's really fascinating here is the why behind all this chemistry. A hydrogen ion is essentially just a single, unstable proton. It cannot exist on its own in water for very long. So when an acid releases this proton, it immediately goes looking for a home. Now, a water molecule has an oxygen atom with two lone pairs of electrons. The lonely proton eagerly latches on to one of these pairs, forming a coordinate covalent bond, and bam! This transforms the water molecule into a positive hydronium ion. Similarly, when a base like ammonia interacts with water, it steals a proton, leaving behind a negative hydroxyl ion. It's just this continuous, invisible exchange of tiny charged particles. Moving on to Section 2, the chemical battlefield, measuring the pH scale. Okay, so now that we know who the players are, how do we actually measure who's winning this invisible tug of war? Well, that's where the pH scale comes in. It's our ultimate measuring stick. pH technically stands for the negative logarithm of the hydrogen ion concentration. I know, that sounds like a total mouthful, but simply put, it's just a scale from 0 to 14 that shows the relative strength of acids and alkalis. Right dead in the middle, at a pH of exactly 7, we have pure water. This is neutral, peaceful territory where the concentration of positive hydrogen ions perfectly equals the negative hydroxyl ions. Anything below 7 is acidic, and anything above 7 is basic or alkaline. But since we obviously can't see ions with the naked eye, we use chemical scouts called indicators. These weak organic compounds actually change color depending on the pH of the solution they're hanging out in. Litmus solution, for instance, turns red in an acidic environment and blue in an alkaline one. Methyl orange makes an abrupt shift from pink in strong acids to yellow in alkalis. And phenolphthalein, it's completely colorless in an acid but turns a bright, vivid pink in an alkaline solution. These visual cues are absolutely essential for chemists to map out the state of our chemical battlefield. Section 3, neutralization, when opposing forces collide. All right, this is the climax of our explainer. What exactly happens when these two highly reactive, totally opposing forces finally meet face to face? Well, the crucial point is the simple but incredibly profound equation. Acid plus base yields salts plus water. When you mix a corrosive acid and a caustic base together in the exact right proportions, they completely neutralize each other's extreme properties. They basically cancel each other out. And what's left behind is a completely new ionic compound known as a salt, alongside perfectly harmless water. Let's actually look at the precise ionic theory of neutralization to see how this chemical peace treaty is signed. The acid donates its aggressive hydrogen ion, the proton. The base provides the hydroxyl ion. When these two meet, the positive hydrogen and the negative hydroxide instantly combine. H plus OH becomes H2O. Water is formed. The leftover ions from the acid and the base are then free to combine into a salt. And just like that, the chaotic tug of war ends in perfect equilibrium. Section 4. The science of salts. The products of neutralization. Now, we aren't just talking about the table salt you sprinkle on your fries here. We are talking about a massive, highly diverse family of chemical products. Down at the molecular level, a salt is defined as an ionic compound formed by the partial or complete replacement of the ionizable hydrogen ion of an acid by a metallic or ammonium ion. Think of the acid as a structural frame holding a hydrogen piece. A metal comes along, kicks out the hydrogen, and just takes its place. That newly built structure, that's a salt. If it replaces all the hydrogen, it's a normal salt. If it only replaces some, leaving a bit of hydrogen behind, it forms an acid salt. To actually work with salts, chemists have to memorize the rules of solubility. If a salt dissolves in water, it's soluble. If it doesn't, it's insoluble. The golden rules here are that all sodium, potassium, and ammonium salts are soluble. All nitrates are soluble too. Most chlorides and sulfates will dissolve, sure, but there are some strict exceptions, like lead chloride or barium sulfate, which will stubbornly just sit at the bottom of your beaker. Knowing these rules is an absolute prerequisite for actually creating these compounds in a laboratory setting. Which brings us to Section 5, Lab Preparation, the Chemical Cookbook. Let's step into the chemical cookbook, where mixing highly specific ingredients yields incredibly specific chemical products. One of the most dramatic ways to make a salt is through direct combination. This is where we synthesize a binary salt straight from its raw elements. First, you place an iron wire coil inside a combustion tube. Then you pass dry chlorine gas through the tube to expel any regular air. You slowly heat the iron until it's literally glowing red hot. The reaction is highly exothermic, meaning it generates its own heat once it gets going, and it ultimately produces iron 3 chloride. So to pull off this synthesis safely, you need a very specific laboratory setup. The iron coil gets heated up and the dry chlorine enters from one side. Now, iron 3 chloride is highly deliquescent, which is basically a fancy way of saying it's thirsty. It easily absorbs moisture from the air and dissolves right into it. Because of this, the final product absolutely must be collected in a receiver flask that is completely isolated from outside moisture, usually guarded by a fused calcium chloride drying agent. It is a super delicate, high-sticks process. A completely different approach is titration. Now, this relies on incredible precision rather than raw, glowing heat. You use this when both your reactants and your resulting salt are soluble in water. You start by filling a long, grated glass tube called a burette with a dilute acid. Below it, you use a pipette to measure an exact volume of an alkali into a flask and add a single drop of indicator like phenolphthalein. You then add the acid drop by drop by drop until the exact moment the indicator changes color. After that, you carefully evaporate the solution to crystallize your newly formed salt, like sodium sulfate. The key to the entire titration process is finding the end point, that exact microscopic moment of full neutralization. As the acid drips down from the burette into the pink alkali solution in the flask below, it neutralizes it. The very instant, and I mean the exact second, that pink color disappears and turns entirely colorless, the tap on the burette is closed shut. At that exact moment, the amount of acid perfectly balances the amount of alkali. It's chemistry that requires the steady hand of a surgeon, for sure. And finally, Section 6, Real-World Chemistry. Acids and bases in action. All right, we're going to zoom out from the microscopic ions and all that laboratory glassware to demonstrate the macroscopic impact of these chemicals on our daily lives. Because this textbook theory, it's happening all around you right now. Weak acids like boric acid are actually gentle enough to be used in eye washes. Citric acid is a super common food preservative. Over on the basic side, the caustic properties of sodium hydroxide are essential for manufacturing the soaps we use every day to stay clean. And hey, if your stomach is feeling overly acidic after a huge meal, you take an antacid containing magnesium hydroxide. It's a mild base that performs a tiny neutralization reaction right inside your own digestive system. But these interactions certainly aren't limited to just your home or your body. They dictate the health of our entire planet. Which brings us to a really critical question. What exactly happens when these delicate chemical balances are disrupted in our Earth's atmosphere on a massive scale? Well, unfortunately, the answer is acid rain. When we burn fossil fuels, massive amounts of sulfur dioxide and nitrogen oxides are released up into the sky. Up in the atmosphere, these pollutant gases react with water vapor. The sulfur dioxide eventually oxidizes and forms sulphuric acid, while nitrogen dioxide forms nitric acid. This means that the rain falling back down to Earth has a significantly lower pH than normal. This acid rain aggressively depletes the soil of its essential nutrients, it increases soil acidity to toxic levels for plants, and it destroys aquatic marine life by radically shifting the pH of lakes and rivers. So, we've seen how acids and bases act as opposing forces, constantly seeking an equilibrium that produces the salts and water necessary for life itself. We've seen how a few dropped protons can create a life-saving medicine, a simple bar of soap, or an environmental disaster. So I want to leave you with this final thought. If every single drop of rain, every bite of food you eat, and every breath you take relies on a perfectly maintained, invisible pH balance, how is chemistry shaping your world right this very second? Keep exploring, keep questioning, and thank you so much for joining me on this explainer.